So let's say we had a room 10 feet by 10 feet by 20 feet, and it's filling with methane at a rate of 10 liters per minute. If you buy a rotometer or a flammmeter for gases, they'll often be measured in liters per minute. So we know the lower flammability limit for methane is 4.7%. So what can we do to work this out? We can use the equation we just showed. Back. And you can say the time it's going to take for this room to fill to get the lower flammability limit is equal to the volume of the room times the percent for the lower flammability limit for our mixture, for our gas, divided by 100, divided by the flow rate for our gas coming into the room. So first we need our volume, and we know we have 10 feet by 10 feet by 20 feet, so the volume is length times width times height. So that's 10 feet times 10 feet times 20 feet, so that's 2,000 feet cubed. 10 times 10 times 20 is 2,000 feet cubed. Now we saw in the units, we need the volume in terms of meter cubed, so we can take 2,000 feet cubed. There is 1 foot is 0.3048 meters. But remember, we need to cube this because this is feet cubed here and this is just a foot. So if we don't cube it, we'll have, if we didn't cube this, we would actually have units of feet squared meter, which are real units, but don't mean anything to most people. So 2,000 times 0.3048 cubed is 56.6 meters cubed. So there's our volume. We know our lower flammability limit. We need our flow rate in terms of meters cubed per second. So right now we know it's 10 liters per minute. That's what we said in the problem, liters per minute. So we can say there's 1,000 liters per meters cubed for 1 meter cubed, and there is 60 seconds in 1 minute. And so this is one of the reasons I like this block method, is I can change multiple units at the same time without having to draw out so much. So we have 10 divided by 1,000 divided by 60. So that's 1.67 times 10 to the negative fourth meters cubed per second. So our time to the lower flammability limit is going to be equal to 56.6 meters cubed times our 4.7% divided by 100 divided by 1.67 times 10 to the negative fourth meters cubed per second, which is equal to 6.6 times 4.7 divided by 100 divided by 1.67 times 10 to the negative fourth. So we're at 15,929 seconds, which is equal to 3,600 seconds in an hour, which is equal to 4.4 hours. So if we're talking about the scenario that we looked at before, and we had this lab was 10 feet by 10 feet by 20 feet, it would have taken 4 hours to flow for the room to reach the lower flammability limit, 4.5 hours. And it's unlikely that the janitor would have been waxing the floors for a room that small for 4.5 hours, so it's unlikely that he was the cause of the leak, the cause of the source. So this 4.5 hours, is it reasonable? Reasonable. That's one of the main things we want to think about when we're doing calculations, right? Is it reasonable? So if we think about a Bunsen burner, we've run Bunsen burners in labs. If you're a student and you've been a student on campus, even in high school we would run Bunsen burners, and you would leave them on the order of seconds, like less than a minute. Less than a minute, you'd leave them on before igniting them. So we know that you can leave a Bunsen burner on for less than a minute without blowing up the room. So there's one data point. And we can estimate that we wouldn't expect it to take days. If we wanted to calculate, if we wanted to estimate sort of how long it would take to fill up the room, we could say we have 10 liters per minute. So if we were going to see how long it would take to get 56 meters cubed at this flow rate, it's going to take on the order of 1,000 times 60, so 60,000 seconds. And so that's significantly more than we have here, and we don't want to fill up the entire room. So is it reasonable? I'm going to say that it is. It seems like a reasonable answer to me.